This video is on ionization energy and how we're going to use data to derive the electronic structure of atoms. Ionization energy is defined as the amount of energy required to move an electron from an atom in the gas state. If we think of the hydrogen atom that only consists of one proton and one electron, we can apply the physics ideas of electrical force or Coulombic force and electrical potential energy. In our formula, we'll designate a proton as Q1 and an electron as Q2, and the distance between them as d. Coulomb's law states that an attractive force is proportional to, so we're going to use a proportionality constant K, is proportional to Q1 times 2Q over distance squared. Now, if we're going to use this for potential energy, we're going to need to change our units, because right now it's just in newtons. So we can think of maybe work, because work is a way we looked at energy in our thermo chapter. And work is just force applied over a distance. So if we multiply our force formula, K, Q1, Q2 over distance squared, we can get the distance to cancel because we're going to have that distance multiplied. That changes our formula for energy, and for this example, it's potential energy for two electrical charges to K, Q1, Q2 divided by distance. If we want to break apart these 2 point charges that are currently held together by an attractive force, we need to apply a certain amount of energy. Think of this as electrical work, sort of. A force applied over a distance. So what we're going to do, we're going to figure out the ionization energy's relationship to this energy stuff we talked about before. We know we have to break the same amount of energy that's holding them together, but it's going to be positive. Weird, but we have to put a negative sign in our ionization energy formula. Well, why? It must be because if we look at the potential energy formula, which was K, Q1, Q2 over D, every time we have an electron in our formula, that electron is going to be negative, which will make our potential energy negative. So if we want to describe our energy as being added, we'll put a negative sign in the ionization energy formula so that the answer will end up being positive. Now that we have a theoretical basis for the concept of ionization energy, let's consider what ionization energies of elements might be. If you assume that electrons orbit in a circle around a nucleus, which is a popular wrong assumption, let's graph what we would expect the ionization energies to be. For this exercise, let's assume that the distance between the nucleus and the electron is equal to the atomic radius of the hydrogen atom, which is about 53 times 10 to the negative 2 meters. Let's do a sample calculation so that you understand where the numbers in our table are coming from. First, we're going to need to know what our charges are. So Q1, let's make that guy our proton. Experiments have shown that the amount of charge on a proton is about 1.6 times 10 to the negative 19 coulombs, coulombs being our unit of charge. Our second charge, our electron, is going to just be the opposite of that, negative 1.6 times 10 to the negative 19 coulombs. Our K value is going to be reported as 8.99 times 10 to the 9th. It'll have units that will help us cancel stuff in our formula, so it's going to be newtons, which is a force unit, times meter squared divided by coulomb squared. Now let's plug and chug these numbers into our ionization energy formula. If we do it for the simplest atom, the first ionization energy for hydrogen, we'll plug in K, which is 8.99 times 10 to the 9. And we'll plug in Q1 for our proton, 1.6 times 10 to the negative 19. And we'll plug in the electron for Q2, negative 1.6 times 10 to the negative 19. And we will divide by our distance, which again, we're pretending everything is the size of hydrogen. So it will be 53 times 10 to the negative 12 meters. Now when we do this math, it'll end up being about 4.4 times 10 to the negative 18 if you plug it in your calculator. But what are our units going to be? If we check all the pieces, our constant K has newtons times meters squared over coulombs squared, and our two charges have coulombs, and our bottom has meters. So what we'll have to do is end up having Newton meters, which is a joule, which is exactly what we want because that's an energy unit. So if we calculate all of our proposed ionization energies, they're going to end up looking like a line. They're going to have a linear relationship. What's weird about this is that it only works if the distance stays the same. If you assume that your electrons are anywhere not the same as the radius of the hydrogen atom, this data won't look like a line. The distance needs to stay constant. However, according to reported ionization energy values, this linear trend does not exist. Here's a graph of the ionization energies for the first 84 elements. You can see that we don't have a line at all. In fact, we have a bunch of spikes and dips and miniature spikes, and then areas with no spikes at all. We have a lot of really, really interesting things happening here. Let's focus on these peaks for a second and the dips. Why are these dips happening? Well, let's figure out what elements these are. The red dots seem to all be noble gases with atomic numbers 2, 10, 18, and so forth. And the blue dots are dips in the data, seem to be the alkali metals, which have atomic numbers 3, 11, 19, and so forth. So this pattern seems to be repeating in a way that looks like the periodic table. Please note that the word periodic means repeating, and we have a repeating pattern. There are a few interesting details about these first ionization energies that can still be explained by talking about electrical potential energy, if we change our model. Recall in our table that we assumed that all the atoms had the same radius between their positive nucleus and the electron being removed. However, this assumption is, well, it's just not consistent with the data. It's not consistent at all. We'll notice that we have a spike at helium, a dip at lithium, and then it starts growing almost in a linear way after lithium, but the idea that they're all in the same distance is not going to fit our data. If the ionization energy actually is K times Q1 times Q2 divided by distance, you need to break the force of attraction between the nucleus and the electron. And these variables, well, at least some of them must be constant. K is a constant that's proven in a whole bunch of physics experiments. Q1 is always going to be our charge of our protons in the nucleus. Q2 is always going to be charge of an electron. That leaves distance as the only variable that must be changing in our equation. Looking again at figure 4, which is this one, repeated again, and the data in table 2, we can hypothesize that the distance between the nucleus and the electron in helium and lithium must be different. Our peak will be helium and our dip will be lithium. But why? If the ionization energy for lithium is smaller, it would have to have a larger distance. If they had the same distance, it would have a greater ionization energy. Therefore, lithium must have a larger distance to lower the ionization energy. It's the only way the formula will make sense. So if we want to draw a little picture model for ourselves, we can say that the first two act normal. They are kind of like heliums. But when we get to our third electron being added, we have a greater distance, or a larger distance. And that is all we have to say about ionization energy. Please don't forget to send me your questions. You can email me this evening, or you can ask me in class tomorrow. Make a list of things that don't make sense. Also, thank you for watching.